People, this is not a dipole antenna. Look, it's a high gain dielectric lens antenna, alright? And this is the weapons delivery system, alright? That's the high gain antenna, illegal high gain antenna. Number of people have contacted Northumbria police about the genocide that's been committed on the people in Gateshead as we speak. Their lenses, so what they do, that creates focus point. These are basically lasers. So this is the equipment. This is a blatant weapons program. It is not a street light. This here is not a motion sensor. People, this is not a dipole antenna. It is not a street light. This thing's quite interesting. Alright, this is a Telenza unit. It's a weapon. It's an absolute weapon system.
This is a 32 cavity back ceramic head. Electronic assault weapons system.
Yeah, this is the cavity back phased array electronic assault weapon. I've just cut the wires there. That's what everybody needs to do. I'll take the unit down.
Where we have identified a weapon system on the pedestrian crossing in High Street Danby. I'm now going to disable these illegal weapons.
That equipment is well able to murder you.
Hello and welcome to the video. If you are new to the channel and you are like, who is that guy holding bits of lampposts and bits of traffic sensors? That, my friend, would be Mr. Mark Steele. And I was never going to do a Mark Steele video again. I debunked him pretty extensively, to be fair. Like, ultimately debunked him. But he's back, and the problem is now, which made me do this video, and not just sit back and watch all this unfold, is he's coercing, or should I say grooming, vulnerable men who are suffering from various states of paranoid schizophrenia and mental illnesses. He's grooming them to attack UK infrastructure. And well, let's just get on with the video, shall we? Let's get on with it. Okay, so this is the unit for testing the ADG 306. This is a 24 GHz radar horn antenna feeding a super heterodyne receiver. This receiver is actually capable of receiving between 9 and 42 GHz. This is the super heterodyne's horn, and as you'll see now, this is the actual super heterodyne circuitry, and it's quite bloody good, and being able to tap into that and get an output around 300 megahertz with 24 gigahertz is a godsend. Yes, so we're going to test the ADG 306 today with our unit, and we're going to debunk Mark Steele, obviously. This is possibly one of the weirdest builds I've ever done. But yeah, so here is our ADG 306. This is what we will put under test, or this device under test. This is the internals, or at least the PCB, or the actual millimeter wave emitter and receiver. And this is our control. This is a DF Robot 40001 module, and we will use this as a comparison to the ADG's power density at around about 200 millimeters. So yeah, let's get on with it. Okay, so now what we're going to do, we're going to test the near field power density of our ADG 306 module. We have a horn antenna. That horn antenna feeds a super heterodyne there, which goes off into a signal to voltage converter, and then that is basically interpreted by a little Arduino, which outprints to my software I wrote that's on the screen right now, and it shows the power density on a graph. Okay, so what we'll do, we'll fire this up in 3... Oh, hang on, I should mention, when I do fire this up, there is a ramp up time, so you won't notice it straight away, but you will notice it. Okay, so 3, 2, 1, go. See, it's starting to ramp up now. You'll also notice how these pulses are really far apart as well. This unit is only putting out around about 7 dBm power. So, yeah. Okay. Yeah, the pulses are extremely few and far between. And they vary in amplitude as well. Right, okay, we've seen that. Now what we're going to do is going to move on and show a different module at the same distance, roughly around 200 millimeters, as denoted by the ruler. Yeah, we're going to test that, and I'm going to show you why this is extremely weak. I'll go into it later in the video as well when I do the teardown. And yeah, it needs a low noise amplifier because the output is that weak, and the actual microwave chip itself has its own low noise amplifier, so it's double amplified on the input side. Which, anyway, that's a tangent. We'll look at that in a bit more depth later. Okay, so I'm going to move on to our DF robot module now, just to give a comparison. Right, let's do that. Turning this off. Just to let that run now. So you can see there's no more pulses, so it is the unit that's doing it. Obviously there's a noise floor there, there's all kind of radio signals in the environment. So I know these videos are long, but this is stuff I have to do as proof. I can't just say, haha, look, that transmitted that, when really I've got a walkie-talkie under the table. So, yeah, this is what I've got to do, basically. Okay, so now it's time to use the DF robot millimeter wave Doppler radar, 24 gigahertz millimeter wave Doppler radar. This is just a off-the-shelf consumer hobby electronics piece of equipment. 4 TX, 4 RX elements, exactly the same elements that are on the ADG 306 unit. Similar Rogers PCB substrate that's got a low dielectric for that kind of frequency. Okay, let's turn it on and let's see what the power density is like at 200 millimeters. Same thing, same setup that the 306 was on. Right. You'll notice that the pulse rate is rapid. Move that a bit too far. I would hazard a guess that the pulse rate of this radar is at least 300-400 times that of the ADG 306. Right. Yeah, so clearly that has a lot more going on than what the ADG traffic light unit does. That's a lot of pulse spikes in comparison. So what I'll do, I'll take a snapshot of this and then we'll do a comparison of the images. Cool. So here is our DF robot C4001 results. Clearly see a high rate of pulse, a high amplitude, and yeah, we would expect that from quite a modern unit in this kind of band. Here is the results from our ADG 306, or should I say the MFG IPS 937. Spoiler alert, we will get to that later. But yeah, few and far between, pulse rate is not that great, amplitude, meh, considering it's 200 millimeters away, is absolutely nothing. So here is a comparison. The blue is the C4001, the red is the IPS 937 unit. You can clearly make out there that the IPS 937 unit is lacking and the DF Robot C4001 unit is dominating. So to put this into a common context, the C4001 unit is a 19-year-old football superstar, smashing the Prem, every European club wants him, he's going to the World Cup. The ADG 306 IPS 937 is that footballer who should have retired, has lost the yard, is still in the game, but yeah, he's not quite there. He's not going to do it for England, or any country for that matter, or any club. He's literally going to Saudi Arabia to whittle out his days for a club there. And the reason being is because the IPS 937 unit is over 10 years old. The C4000 unit from DF Robot is about 2 years old. So, how is this a weapon? If a consumer hobby electronics millimeter wave 24 GHz Doppler radar can outperform it, how is it a weapon? It's clearly not, is it? Anyway, let's move on to the next section of video. It's very bloody interesting. It's not going to do anything, is it? But what I'm going to demonstrate lastly with this unit, so this here that you can see and here, this is to stop reflection. This is a high dielectric constant material, and this material is used in shielding and to protect electronics as well from, well, stuff like ESD, radio waves, all manner of, you know, emissions. It stops at X-rays, obviously, because X-rays would just go through that like it wasn't. Although it probably would cause some Compton scattering, but you know, let's not go down that route. But yeah, so I'm just going to do, I'm going to bring this round to this position here. It's hard to see on the camera. Okay, next to the unit, and we're going to fire it up, and it's only 12 volts, I'm not going to electrocute myself. Now there will be reflections of all this stuff. In fact, let me move this. So these materials effectively are just stopping it from reflecting off what you can't see it on the video. But there's I've got like loads of electronic components in like a bunker back there that it will reflect. I'll move this as well. This bit of steel can get out of the way. Right. So the reason why these radars work is because they reflect off human bodies, i.e. my finger's there and it's already reflecting. So that's not reflecting now. If I move my hand into that position, remove my hand, move my hand back into position, and as you can see, there's only a slight loss of energy. On the reflection. Remove my hand. Yep. So there's only a very, very minuscule loss, and the reason being it's reflecting off me, it's not entering me, it's not cooking me. 24 gigahertz reflects off. Right, get rid of that. And I can finally turn you off. And I can unplug you. Right. Okay, so that 24 gigahertz is reflecting off me, it's not penetrating me. If it was penetrating me, as you can see on the graph there, you would see a far greater loss. Now, there is some scattering and loss because I am not the perfect reflector. There's water in my skin, so some radio waves will be refracted off. Some will bounce at that angle into the horn antenna. But the loss is very, very low. So, as you can clearly make out, hang on 1 minute, just stop that running. As you can clearly make out, it's reflecting off me. It's not penetrating my skin. It's not cooking my insides. The reason why they are there is to reflect. It's a radar. A radar needs a reflection from a target to work. Okay, it can't penetrate your body. And for something that apparently has this ceramic stop it getting hot, I ain't burning, okay? But before we continue the debunking of the ADG 306 unit, let's just take a trip back in time to a unit that Mark Steele, which was in the intro, said was basically the same as what the ADG 306 unit was. It adorned street furniture. It was implemented by councils to save money. Let's go back and revisit it. If you are a regular to my channel, you will know this unit, but I just thought it's a goldie but oldie, and there was a few things I didn't do in my original debunking video, which I'll leave at the end and in the description. But let's just rewind. Okay, so an oldie but goldie. We're going to revisit where it all started for Mark with this lamppost light telemetry system. 868 megahertz. You probably know this already. If you're watching this video, you're probably really aware of what he was saying about these units. I've debunked this in a previous video, but there's a few little things that I'm going to address in this one I didn't in that one. So yeah, we're going to revisit this. What we're going to do is, or should I say what I have done? One moment, please. I have soldered some connectors onto these aerials, which are basically this aerial. Now I'm going to put them on a vector network analyzer, and we're going to look for loss tangents. And basically I'm going to have it so it's either strip to strip, the PCB material, which is FR4 to FR4, and also FR4 to strip. And I've put some marks on there so we know those two strips line up. This is perfect for a network analyzer because as a material under test we can do a free air test with these, and basically there will be differences in the loss between them, which is absolutely great. Yeah, I'm just showing the dielectric loss and dielectric constants of these materials, and also as well we have our wild card, which is cardboard. So we'll do a strip to strip but with the cardboard in between, just to show that, you know, something with a similar thickness has a similar loss. And at the end of that we should show that these are omnidirectional and aren't some kind of death ray that's directing some radio waves at people and can track people, and it's an urban, what Mark called these was an urban scanning radar system. Well, to put that into perspective, we have a SI-1000 telemetry chip in there. This is for my T800 drone, which is a big drone. This is the telemetry system. So I get a feedback. It tells me all kinds of parameters that the aircraft's going through, altitude, yaw, everything, ground proximity, the works, and I can send commands via a PC or a phone, via a flight manager system to the autopilot APU system, and I can instruct that what to do via this module. This is the exact same SI-1000 that's in there. So apparently my drone is an urban scanning radar death ray when it's got this on board. I have a Civil Aviation Authority license, a pilot's license. I think the CAA would revoke my license if I was flying heavy lift drones with telemetry units which were technically weapons. Okay, but anyway, we'll get this on the microscope and we'll have a look. We'll do the vector network analyzer tests to look at the loss tangent of this FR4 material and obviously various configurations. Yeah, and we'll get on with that. And before I do that, I'm going to enjoy my beer. Okay, let's crack on. Right, so let's take a look at the chipsets then. So this is, as previously said, the SI1000 on my drone's telemetry system. There we go, SI1000, made in Taiwan. This is our Leaf Node. Let's just have a look. I'll just focus in on that. SI1000, made in Taiwan. Defray, so they say. Okay, so revisiting Mark Steele's claim about these antennas, as we've just previously talked about. So these now are on the VNA. They are microstrip to microstrip antenna. And we can see there we have a return loss of about 2.7 dB and a gain of negative 14.6 dB. So that is strip to strip, as close as that strip can get. So what we're going to do now is just going to take these clips off, separate them out, and we're going to go FR4 material to FR4 material on the back. I've put 2 dots there to make sure they're perfectly lined. Get these on so my hand isn't doing anything. Right, that's that, nice and square. Okay, so the return loss has gone up round about less than half a dB. The gain has dropped off by around about 1.5 to 2 dB. So yeah, okay. So that's FR4 material on the back of these to FR4 material. So what we're going to do now is going to rotate that round like that. And have, oh, I'm getting a bit confused here. There we go. Okay, yeah, like that, which is bloody awkward with these stiff cables. So I'm just lining these up again. That's pretty much lined up. Okay. There we go. Nice and square. So you can see the return loss now is 3.4 dB and the gain is around about 12.5 dB. So that's strip to FR4 material. Cool. And obviously what we'll do now, we'll just reverse that to the other one. Let me show you what's like there. Line that up. Cool. So yeah, same again. Return loss 3.5 to 3.6. And our gain has not really changed that much. So what Mark's claiming about these is rubbish, because he was claiming it's directional. It can, you know, basically it can target acquire. It's directional, but it's not, because there's hardly any loss. And to prove that, the FR4 material these are made out of. So again, if we go, let's go. Yeah, all right. This is a bit of a trick of the mind. Okay, so what I'll do is I'll get that back to how it was there. And same again. Let's get that pinned on there. Move that up so there's no reflection, like so. There we go. Right. So that is strip to FR4. Cool. Cool. Okay, so return loss is 3.2 dB and the gain is 13.3 dB. So that's strip to strip. So what we'll do now, we'll take that off. We'll rotate these round. Sorry, that was strip to FR4. Now this is going to be strip to strip, but what we're going to do, make sure these are still tight from all this rotation, what I'm going to do is I'm going to introduce a bit of cardboard as a spacer. Get these together. Oh god, this is really difficult. I need to just have a quick look to see. I think we are, yep, lined up on the dots. We are now. So I'll get a clip on, get it nice and square. Like so. There we go. Square you guys up. Yep. And one on the top for you. Alright. Square that up. So this is strip to strip with a bit of cardboard in the middle. And would you believe it? Return loss, 3.4 dB. Gain, well, slightly higher gain, but not by much, by a fraction of a decibel. So clearly the FR4 material, which Mark says is a dielectric, is no different to a piece of cardboard being between the strip to strip. And we've just shown it, you know, the really, really low dielectric constant FR4 material, i.e. the 4 denotes its dielectric constant, which is 4. And that cardboard is probably a similar dielectric constant to that. The loss is obviously different between different materials, but these materials give the same loss as the FR4, i.e. it's the distance. That material is not reflecting those radio waves. It's not a directed energy weapon. It's not directing that energy at you, because the return loss and the gain is very, very small differences there. That would not be the case if this was a high dielectric constant material that could theoretically, like aluminium or something like that, that could theoretically reflect those radio waves. Then we would notice that the loss would be huge. But it's not. It's an omnidirectional antenna. It's basically in all directions it's radiating. It's not, you know, some magic thing. And that on the end is just conformal coating. So yeah, hang on, camera. Yeah. Conformal coating. And I had to revisit this in this video because he's making more bullshit up about antennas. But as we just proven there is pretty much no loss apart from the distance that this acquires when there's 2 bits of FR4 material between the antenna. Obviously, it's VNA. This isn't really transmitting a strong signal. All this is doing is effectively just looking for dielectric constant, just looking for lost tangents and stuff like that. It's not actually a transmitter. Technically, it is a transmitter, but not a very strong one. So it's very easy to test the magnetic field between these 2 elements. And to be fair, these lend themselves perfectly for a material under test in what's known as a free air test or an open test. And yeah, they just line up perfectly, and we've just proven there that, you know, there is no loss, effectively. Slight loss, but that's due to distance. Yeah. Clearly not a weapon. Okay, moving on. Well. Wasn't that the trip back in time? Let's do the time warp again. It had to be revisited, because Mark has been debunked about these units. And not only has he been debunked over and over and over again, but what he's currently claiming is just the same repetitive verbal diarrhea he was spouting all those years ago. It's exactly the same. It's street furniture. It's a weapon. You don't understand it, so therefore I'm going to tell you it's trying to kill you, your family, your friends, and instigate some kind of pseudo-anarchy that only exists online but has now started leaching out into society, as we have previously discussed. And he's literally using this to groom grown men. Yes, I know, it's astonishing, it's crazy, but these grown men clearly are suffering from various levels of schizophrenia. Mark may not, or may know, that they do. Now I hope it is the former and not the latter, because if he knows these people are suffering from schizophrenia and he is exploiting them to commit these criminal acts against infrastructure in the United Kingdom, that's a massive problem. But anyway, moving on. So we're going to test the ADG 306 now. We're going to use a thermal imaging sensor to see its infrared output. Basically, how hot it gets. So Mark's claims are, he claims that this is ceramic material because it gets so hot. Well, let's put that to the test. Right, so what we're going to do now is take a thermal image. See, Mark claims that this ceramic is there because it gets extremely hot. Let's put that to the test. Okay. So, it's 24 degrees today. 22. Oh yeah, 22.5 again. 21. 22. Right. Now we're going to switch the unit on. Now. Okay. So you can see the spikes. Okay. Yep, so there's not much change there. As I say, the ambient temperature today is around 24 degrees. It's obviously a bit cooler indoors. The max temperature at the top is from a PSU's behind, powering this. Yep. Right, turn the unit off. Now go back in. We've already took cool temperature, but, well, there is no difference really. Yeah, okay. So, that did not get extremely hot, did it? So again, getting ceramics and low dielectric constant materials mixed up when, you know, the ceramic has a high dielectric strength to resist electricity, current. High dielectric constant materials are not like that. They are there basically to allow the free flow of photons, i.e. radio waves. Okay. Well, that's obviously bullshit as well, so let's move on to another bit of debunking, shall we? Okay, so we're now going to look at the actual continuous wave radar module itself. In particular, we're going to look at these two chips here, or these two IC packages. This, to me, looks like it could be a low noise amplifier in. And then this here is our actual 24 gigahertz constant wave chip, and that's your TX out there on that side. So that's your TX, that's your RX. So we're going to look at these packages. We're going to get some data sheets done, and then we're going to go through it. So let's find out, shall we, what these are. So if we come to this first one here, let's get it in the light. We have a LNA. Hey, I'm good. LNA 004. Our other package is a... let's have to just focus in on that. A LTR11. So that'll be our microwave chip. So let's concentrate first on the LTR11. Okay, so this is our user guide for the BGT24 LTR11. This is made by Infineon. It's basically what it says on the tin. So it's a 24 gigahertz MMIC and helps users quickly. Well, this is talking about the document itself. Intended audience is obviously programmers, etc., and people, you know, want to get involved in the design of these boards. So table of contents. So we'll go straight to transmitter on page 4. Oh, cool. So there's some good schematics there. That's pretty cool. Cool. Right, transmitter. Aha, cool. So we've got a TX power output versus temperature. So let's go for 25 degrees C, which is purple, which is here. So in the 24 gigahertz band, we're peaking where it is really 20 gigahertz, 125 megahertz, whatever it is. We're roughly 7 dBm. Okay, so this is Wi-Fi router power territory, really. 100 milliwatts, something like that. Cool. The receiver gain, well, the conversion gain, let's say, same again, 25 degrees. So the gain basically is near enough, call it 3 times the dB as the transmitter is. So this is obviously got its own, it says there at the top, it's got its own low noise amplifier, before it comes to its mixer. And if we take, like, say, 25 degrees Celsius, we're talking what, like 21 dB gain. So it pulls in more than it puts out. So it puts out 7 decibels, and its gain is about 21 decibels at 25 degrees Celsius. So it clearly needs a low noise amplifier to receive the return, because the return's going to be extremely weak because it's only 100 milliwatts, and this is going over, like I said before, 120 meters. So it's no power at all. It has to have this input amplifier or this receiver amplifier or low noise amplifier. It has to have this to work. Without this, that signal would not be able to detect the signal. Okay, so let's move on to our other chip on the board, which is our low noise amplifier. Let's just focus down on you. There we go, get that. LNA 004. Okay. Right, so what we'll do, we'll get the data sheet for that. Okay, so we have our data sheet here, and let's just go through it. So this is Silicon Radar made, which is a German company based in Frankfurt, Germany. There we go, our LNA 004 low noise amplifier in silicon germanium technology. Yep, cool. Simple stuff, date of issue, manufacturer. Okay, so it's version 2.3 to 2019. Yep. Right. Okay, so it's just going through the chip. It's a LNA for 24 gigahertz ISM band, supply voltage 3.3, it's pulling 18 milliwatts. Cool. Yeah, applications, wireless communication systems and radar systems, ISM band at 24 gigahertz and ultra wideband systems at 29 gigahertz. That's quite a bloody range on it. Cool, okay. Just a block diagram. Good, got a control bias. Yeah, and some separation there, possibly microwave separation, just for filtering. Yeah, go down. Cool. RF in, RF out, power, ground, VCC, voltage control, ground. Cool. Nothing much to write home about there. 50 ohms, as we'd expect, RF outputs. Otherwise, it would seriously damage the system if it's not 50 ohms. Cool. LNA gate control, high, low, CMOS logic input. Yeah. And then obviously you can have a resistor, pull down resistor. Yeah, just to get it going, so you don't need to attach any kind of MCU to it. It's just going to do its own thing regardless. It's just a dumb LNA basically. It's just an amplifier to amplify it. And as we said before, with the actual transmission chip and the actual radar chip itself. That was 21 decibel gain with its own low noise amplifier. So this system needs another low noise amplifier on top of the low noise amplifier in the chip. That just goes to show how weak the signal from this is. As we proved with the bacon experiment, which, to be fair, it could have been putting out 100 watts. It still would have reflected off the bacon because it's 24 gigahertz. That's what it's designed to do. It's designed to reflect off stuff, not be absorbed by stuff. Otherwise, it'd be a pretty crappy radar, let's face it. Okay, so, yep, DC voltage, blah, 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 blah. ESD robustness, 500 volts max. It's a class 1A, so you handle this with your bare hands. It should be alright, but just be really, really careful. Goes down to minus 40, 85 degrees Celsius max, top temperature. Supply voltage, yeah, about 3.3 volts between the min and the max. DC voltage, blah, 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 blah. Thermal resistance, not really applicable to what we're doing. What is though is down here, so we have our RF parameters, frequency range, which that is a really good bloody range for an LNA. Output impedance, obviously 50 ohms, has to be. Number of gain settings, it's two settings controlled by voltage control. LNA gain, okay, so minimum is 13.5 decibels, maximum is 17, and high gain, low gain is obviously 6.5 through 10. So this is adding on top of the 21 decibel gain that the radar chip that we've previously looked at has. This is adding another 17 decibels of gain. And as I say, that's how weak these output. They're not very, very strong. And it needs that massive amount of gain to receive the return signal. And we go down to the package. Yep, nothing outstanding here. Obviously just this for reflow when you're soldering. This is what we want. So let's get our chip. Get it there. Okay, so looking at the schematic, I think this, it is, yes, because this is RF out, and this is RF in, so this is upside down. So if we look at pin 16 on this side, that's identical to the application circuit schematic, or the example circuit. We pop over, we've got 2 ground, yep, we've got a high-low gain, cool, and then if we go up, there we go, that's our power in, ground, power in, so we've got RF in, RF out. That is pretty much barring maybe 1 or 2 components missing there, but do you know, I don't think there is any components missing. I think we're pretty much on it. capacitors there. I think... Wait, no, not capacitors, sorry, resistors. Where is it? Hang on. Let me get light on this because it's hard to see. Yeah, there we go. There's our capacitor there. There's our resistor. Yeah, so that's our gain. And there's our capacitor there. Going to the 0 volt rail. I think, I don't know whether the capacitors on the schematic are just a representation, but yeah, we've got one here. Maybe, there we go, because there is some, maybe that's replicated up here somewhere. It's hard to tell because of the layers of this board. It really is. But yeah, it's pretty much the same as the schematic. And that's that. So what we're going to do now is going to look at the PCB material itself that this radar module is made out of. Because Mark Steele claims that this is some kind of, dielectric like he does. But I think he's getting confused. I think he sees the word dielectric as dielectric strength, i.e. voltage, electrons. What we deal with when we're dealing with radar systems and, well, RF in general, is dielectric constant. So FR4 PCB material has a low dielectric constant, but it's too high for microwave applications. And we're going to look at the PCB material here, which I suspect I know exactly what this is. Well, I do know what this is. I don't suspect shit. I know exactly what this is, but Mark Steele doesn't. And yes, there is ceramic in it, but it's not the ceramic that has a high dielectric strength. It's ceramic that has an extremely low dielectric constant. So we're going to discuss later the difference between dielectric strength and dielectric constant, just to cap this off. But for now, we're going to look at the material, and I'm going to go through what the material is. Excellent. Right, so let's crack on then. Okay, so now we're going to look at what material this 24 gigahertz continuous wave module is made out of. So here we have our Rogers. Oh, sorry, it's really difficult. It's so small. This is our Rogers RO4000 PCB material. This is also Rogers RO4000 PCB material. This is a pin, by the way. This is our FR4 material here, PCB material in the middle. And we can see that FR4 material if we rotate it back there, that green coloured stuff there. Cool. And then obviously on the front side, I'll focus. This is our Rogers RO4000 series material. And as you can see, we can see the green tinge. It is that thin under this light. We can see the green tinge of the FR4 material coming through. Yeah, so that's what that is. It isn't any kind of special dielectric strength ceramic. This is a low dielectric constant material, i.e. Rogers RO4000 series. So it could be 4001, 4002. It doesn't matter. It's designed for microwave applications. And it's that thin you can see the green tinge there coming through. You can see the green tinge coming through from behind the antenna element. It's that thin. Really, really thin. And you can see it there. But yeah, it's not as Mark Steele says, a ceramic. It is a hydrocarbon ceramic composite that's basically built for microwaves. That's what that is. It's RO4000 material from Rogers Corporation. And you can see how it's a composite. It's not a solid ceramic. And the reason why is for its low dielectric constant. So, is it a true ceramic with a dielectric strength, i.e. electrons, voltage? No. Now, having a low dielectric constant, it's perfect for radar applications because it's not going to mess with the signal. So we have all kinds of filtration on the back of the board. Let's focus a bit better. So on the back of the board here, you'll see, get my pin, you'll see this little fella here. This is all microwave filtration. And there will be one on the other side. More filtration. So this is why, and as you can see again, the green tinge is even better on the back, coming through from the FR4 material underneath this light. And you can see there how thin it is. You can see the strands that hold it together of the composite material. It's not a true ceramic. There is no way, sorry, I got the pin in my mouth. There's no way in God's green earth that is a true dielectric strength or a strong dielectric strength ceramic. It is a low dielectric constant ceramic, which means radio waves can freely pass through it. So what Mark is saying here is ultimately bullshit. Mark is using the premise of a dielectric strength, i.e. voltage, current, electrons. This is not this. This is radio waves. This is photons. Photons are completely different to electrons. And yeah, that is that. Okay, so this is Roger's Arrow 4000 series high frequency circuit materials. So it is a hydrocarbon ceramic laminate, and it's clearly telling you there it offers superior high frequency performance. Basically it's better than FR4 or PTFE. It's a good material. So we look at, the different types here, and we can see its dielectric constant. So it's versus temperature, and these are extremely low dielectric constants. So if we look at the dielectric constants of the RO4350B material we are dealing with, it is 3.66, whereas the FR4 material for PCB is, well, it's called FR4 because it's got a dielectric constant of 4 or there or thereabouts. And that's for 8 to 40 gigahertz. So yeah, that's the reason why that's in there. It's to allow that radio wave, or allow the radio waves to pass right through it. There's nothing remarkable here. So in this image we have here, we can see that this is a kind of true ceramic with a high dielectric strength of kilovolts per millimeter, and we can see that the dielectric constant is 9.8, 9.9, 9.9. This is alumina, which is your bog standard ceramic that has a high dielectric strength. So here we have our oxide ceramics. We have aluminium, ZTA, zirconta, beryllium oxide, aluminium nitride and silicon nitride. And as you can see right across the board for the dielectric constant, they are extremely high, whereas dielectric strength is also extremely high. So this is where Mark Steele is getting confused between constant and strength. Now, a dielectric constant is a measurement of how well a material attenuates or absorbs the RF component or the photon component. Dielectric strength is how well it absorbs electrons, the electronic component, or the voltage current component. In this case it's DC, but that's irrelevant. And you can see, they're quite strong absorbers, whereas also the dielectric constant is too strong for radar systems right across the board. And okay, beryllium oxide, yeah, that's really, really low, but yeah, good luck working with that. We come close with silicon nitride, but yeah, come on. But yeah, that's basically where he's going wrong. He thinks it's dielectric strength, not dielectric constant. Okay, so that was the teardown of all those components on that board. And I originally thought that ADG made this as a proprietary system. Well, spoiler alert, no, they don't. Well. Our urban scanning radar, depth ray, cavity backed, whatever, is just an off-the-shelf component. I originally thought that ADG did this in-house and was proprietary. No, it's not. It's made by a company in Germany called Innocent, and you can purchase one for the grand price of £86.32. I literally just found this. I was actually the other module, the DF Robot 4001. I literally googled that because I was after some specs for it. Literally specs for it. And then I thought, I'll just check the images because I needed an image, obviously, to do, as you would have seen prior to this, to put into the comparison for the output of the field strength and power density. And I needed an image, so I went on Google Images and it was there, and I was like, oh my god, what is this? And it's literally, I can get it off DigiKey right now, I can get this off DigiKey right now for £86.32. I thought this was in-house, made by ADG in the UK, and it's not. It's made by a company who mass produces them in Germany. They're like, I didn't even need to do this debunking video, I just needed to find this. And yes, there is a datasheet. So Mark is claiming here on Facebook that this is a 5G antenna, and that the criminals in the local authority say it doesn't exist. Well, spoiler alert, it's not a 5G antenna. That there is an expressive ESP Wi-Fi module, or 2.4 gigahertz Wi-Fi module. Anyway, let's check it out. Mark claims that the chip in the back of this chip here, is 5G. That's what he claims, connects to the 5G network. Okay, so I've already got the MAC address off this ESP unit. So it's an ESP unit. It's basically, you find these in everything. They're in Ring doorbells, they're in remote control cars, they're in anything that's like 2.4 gigahertz that you want a secure connection between. Okay, so to prove that, you'll notice at the top I've got a command ready to go, some syntax. So just to go through this, we're using aerodump, which is part of the aircrack suite, available on Linux and Windows. The text, or the long string of text after that, is actually my Wi-Fi card. Now, why Canonical and Debian change that from just like WLAN1 or MON1. I have no idea, but anyway, that's a tangent. And after that is our BSS ID, which is our MAC address for our unit. So if I execute that command, it'll take a while. It just hops through the channels to find it. There we go. That's the unit. Now, the reason why that chip's in there is when you set these up, there is a browser interface within that chip written in HTML that you can log into and you can change parameters. But this is acting as an access point. It's not a client transmitting back and forth. It's what's known as an AP, an access point. We can tell that by looking at that there. I mean, it's got an encryption suite. It's got its authentication is PSK. That is 2.4 gigahertz Wi-Fi. That is not 5G. And it's an access point. It cannot act as a client. It can be one or the other. It can be an access point or a client, and that is set to AP, access point. It is not 5G, it's not a client, it's not communicating with other equipment. Basically, you can add this as a Wi-Fi AP to your phone, log in, and then you can change the parameters. And that's it there. It's a ADG 306, and you'll notice the ESSID is 306. That's denoting its serial number. So yeah, that's that. And what I can do now is just Control-C that out, turn the unit off, and then I can recycle this command. We'll just leave this running for a little bit. I know it makes these videos longer, but these are the things you've got to do just to prove that, you know, I've not got something else that's transmitting that particular BSSID, ESSID at the end there. Okay, so this is basically considerably longer than what we waited before. So I'll power the unit back on. I say it's just to prove that I'm not mucking about, not making it up. So it's looking for the MAC address, or the BSSID. There we go, channel 6. Yep, so that is that. Yeah, it's a Wi-Fi card. It's not 5G, Mark, is it? Okay, so that concludes part 1 of the video. Part 1, you say? Jesus Christ, there's more. Oh, there's way more, and I can't fit it in, and I literally pushed the envelope here, tried to keep it under an hour. It's impossible. I cut, I chopped, I changed. See, these people go on and on and on and on and on so much that you just cannot squeeze this content into a 14-minute video. I wish I bloody could, but I can't. It's impossible. The things I have to technically break down and address. It's just absolutely mind-boggling approaching these videos. And I do these unscripted, right? I'm sat in, I don't have a script, I am just talking from my experiences through life in tech and obviously working with radar and stuff, and I just do it unscripted. I just literally press record on OBS or some other software, and I just sit there and I think, right, okay, we need to describe this, we need to do this. Right, that's explaining that, and I am apologetic that you had to watch this if you got to this point. If you didn't, and you just flicked through in the description, good for you. I would do that, to be fair. But man, these videos are so long because of what I have to do. Okay, this now brings me to the closure of the video. The conclusion. And as always, the conclusion with Mark Steele is one word. Bullshit.